Good afternoon or good evening, everyone. Welcome to the presentation session dedicated to scheduling problems with academic use of Kubernetes, called Using Kubernetes in Academic Environment. My name is Viktoria, and I've prepared the article together with Dalibor and Lukas Hejtmanek from Masaryk University. First of all, many of you actually don't know what is Kubernetes, or maybe know just a little about it. So I would like to tell a bit more about it. Kubernetes is a leading open source platform for container management and orchestration. Now I'm citing from a Docker site where I would like to explain what's actually a container. A Docker container image is a lightweight standalone executable package of software that includes everything needed to run an application, code, runtime, system tools, libraries, and settings. Therefore, it is quite straightforward to understand that utilizing container technology in academia can hugely ease researcher lives by hiding complexities, modern software, specialized programs with numerous dependencies, and at the same time, they also provide reproducibility, which is now becoming a European standard in relation to open science. Kubernetes uses declarative approach, so just have to define a state and whole platform ensures that the state is reached. Kubernetes deploys Docker containers in so-called pods, which is a type of object in Kubernetes. And from the moment of the deployment, Kubernetes manages whole pod's lifecycle, starting in the pending phase, then going through running and ending either in succeeded or failed. Monitoring status means that Kubernetes is actually checking whether a pod that should be running is actually running. And if not, Kubernetes is able to restart containers to handle some kinds of faults and track different container states to determine what action should it take to make pod run again. Our local installation at Center CERIDESC at Institute of Computer Science of Masaryk University is composed of more than 200,500 CPUs with more than 9 terabytes of RAM in 20 nodes. So we could classify our cluster as a big computational cluster. Usually, academical computational infrastructures are provided in the form of high-performance computing through some grid execution engine. Container infrastructure is another type of infrastructure that can be used alongside high-performance computing to support large computations, but there are key differences between batch workloads and Kubernetes workloads. The most outstanding and obvious difference would be that Kubernetes workloads are usually used for long-running services, and therefore there is no strict requirement for a runtime limit, or you don't have to provide any precise resource requirements. Actually, no one expects that Kubernetes workload will sometimes end. On the other side, when we are in the batch world, these workloads required specifying maximum runtime limit and also resource requirements, and without that, your job is not submitted. And if you use more than you requested, your job is terminated. This is one of the crucial differences because Kubernetes scheduler can't effectively create queues and predictions about workloads and free resources simply because it does not know when and actually if a workload will end and how much resources it will need. Another difference that we observed in Kubernetes environment is that it is quite convenient for interactive jobs compared to batch environment. but I will talk about interactive computations a bit later. Now, I would like to continue a bit with comparison of batch and Kubernetes environment, and we can take a closer look on batch infrastructure. In academia, or at least in the Czech academia, infrastructure is owned by an organization and resources are provided seemingly for free, let's say, to researchers. Of course, someone is paying for them, but researchers can use them freely for their needs. And it is essential to preserve fairness, and complex algorithms and rules are in place that ensure certain level of fairness. Such rules and concepts are queues, which are ordered by priority. And user priority is then dynamic. So when user is waiting, he has bigger priority, and when user is computing, he has lower priority. Over a long time period, users' share is balanced with other active users. And generally, we could say that scheduler decides who gets the resources and when. On the other side, when we take a closer look on Kubernetes infrastructure, no, the same does not apply. Compared to owning resources, it is more common that user rents or purchases resources from infrastructure provider, and this is known as pay-per-use model, where you pay for what you use. For user, it seems as a great deal, but for organizations owning those resources, it is even a better deal and a perfect opportunity to overcommit unused resources and generate more profit. It is assumed that the resources are not used at every second, and that users tend to overestimate resource requests. From business perspective, there is no need for perfect scheduling because you are actually profiting from that, but you need rather good capacity planning. For example, these infrastructure owners should and can predict times such as Christmas or Black Friday or Super Bowl, when load increases and some services must have a high quality of service and can't interfere with others. However, the rest of the time, it is possible to overcommit resources and assign some lower quality service to these overcommitted resources. And if they are needed, just terminate the service. Generally, we could say that user who provides the money is a scheduler, and that there hasn't been a need for sophisticated scheduler yet. Now, we obviously represent an academical environment, which is not a commercial provider. Therefore, we require strict resource limits to not waste resources really heavily. In addition, Kubernetes features some really basic scheduling mechanisms. For example, resource quotas, which are constraints that limit aggregate resource consumption. These resource quotas can be applied on namespace or on pod, or both on pod and namespace. And if they are applied on pod, I would like to add that we know either limits or requests on resources. And if these limits and requests are applied for pod, the pod is guaranteed the requests, but the upper bound limit is just best effort and may happen and may not happen. Secondly, Kubernetes has static priority classes, where basically higher priority pod evicts lower priority pod if needed. And thirdly, Kubernetes has an object type called job that is roughly similar to batch jobs in terms of that it must end sometimes in the future. So now you might be asking, are there actually any problems with Kubernetes scheduling? Well, of course, there are a lot of them, and they might not be apparent instantly, but we identify them, and now I would like to briefly discuss them. Specifying precise job resources is a key precondition for effective job scheduling, but container orchestrators are not really strict about the necessity to specify these resources. And even if user specifies some job resource requests, there are no guarantees how exact they are. As a result, it is very common that users tend to significantly overestimate resource requests, which has several reasons. I was wondering what could be the first one, and I learned from some colleagues that it is the obliviousness to the concept or logic behind resource specification, when these people just cannot realize how much is one CPU or two or five. Another reason can be user-induced overestimation that causes very low real cluster usage. According to our experience, the overestimation problem is more coupled with Kubernetes workloads than HPC, where the actual ratio is better because users experience job terminations if they cross the limits. So they are more careful about it. And in the figure, you can see the normalized total used CPU hours and the requested CPU hours per namespace, per Kubernetes namespace. And we can see how poorly are the resources allocated and how they are poorly used. Nearly 60% of the namespaces use less than 5% of allocated resources, which is a black line in the image. And the fact that some namespaces use more than 100%, which is a red line, is caused by the Kubernetes allowing pods to have their CPU limits greater than guaranteed. Second reason for huge overestimation are long-running jobs typical for scientific computations. And I distinguish between two types of long-running jobs. First type are long-running jobs, or better say services, that are run something like 3 times a week for 2 hours. And second type are computations that are actually long and are characterized by dynamic variation, when most of the computation requests low resources, but there are short time periods, perhaps more complex parts of computations, when resource consumption spikes. And I think that a good example of this are Nextflow pipelines, which are composed of more parts, and there are parts that require, for example, 1 CPU, and there are parts that require 5 or like 50 CPUs. And usually users fear that their jobs will exceed allocated resources, so causing job to terminate. And they rather specify substantially more resources than experience the situation and the need to run the job again. The correct practice for complex workflows could be probably splitting the job into several units with tailored requirements, but that requires work on the user side, and it's less likely to happen. But there is not an easy solution for long-running services that are used just sometimes, but are required to run always. Some web services that allow you to spawn a small computation. As I already mentioned, Kubernetes is a convenient environment for interactive jobs compared to batch scripts. However, it creates a scheduling problem on its own. When computing interactively, you can imagine that you don't want to wait for another 10 minutes or 1 hour till your job starts, but you want to do it either instantly or in the next 2-3 minutes, because in the end it's interactive. And in Kubernetes, we have observed that it is typically a matter of 3 to 4 minutes until just enough resources are freed and interactive jobs can be executed. However, it can quite easily happen that resources are not available and the container must be terminated, like a different container, any container. And when this happens, it is important to decide what workload types can be terminated in order to accommodate new job. And at the same time, you have to watch out for already waiting jobs that might require just slightly more resources than your new interactive job. Watching all waiting pods is important because you can very easily experience pod starvation. Imagine the situation where you just keep on preferring interactive jobs because of their nature. So you always deploy interactive job, and there are other pods with similarly small resource requests, but they are not interactive. So they are never run, even though they are small. And even bigger problem is that you can end up with pods with larger resource requests that never start because you either prefer interactive or prefer interactive and small resource requests, or just completely forget about the large resource requests because the nodes are never really empty. I just mentioned 3 problems that can be scrutinized in long discussions, and these discussions are already taking place in the community, but the community, the Kubernetes community, has not been able to agree on a solution yet. So we kind of propose a few ideas that can be considered as well. The first proposition is utilization of scavenger jobs. Scavenger jobs are small jobs that can be evicted or terminated when they are needed without any questions asked. They are here to help utilize free resources, and scavenger jobs will be of any effect only when new pods have low resource requests and they are allowed to scale up, which means demand more resources. However, currently pod restart is requested for scaling up, which is not a problem for a microservice or a web service, but for a long scientific computation that has been running for past 20 hours, it is a problem. Such computations are rarely designed for horizontal scaling, and usually they do not implement any checkpoints. But recently there has been a work in progress in community, and there are both talks and actual actions and implementations of both changing resource requests without restart and also implementing checkpoints. It should be in beta version, in next version of Kubernetes. Second proposition from us are placeholder jobs that evict scavenger jobs and are actually a little nice trick to ensure that there are enough free resources that can be used by user spot. A scavenger job is a job that reserves resources, but it does not consume them. A placeholder job terminates existing scavenger jobs, thus it frees resources for the demanding pod. And using node affinity, we can easily ensure that the placeholder job runs on the same node as the pod that needs more resources. And lastly, the last section, naive solution that proposes itself is creating separate clusters for different workload types. It was actually the first idea that came into my mind when thinking about these problems of different workloads. However, we can all think about many problems that happen when you have a lot of separate clusters with tailored schedulers. So you reach an optimal scheduling strategy. First would be large fragmentation issues. Second would be significantly more work for both infrastructure administrators and users, because they would have to decide where they want to actually run their workloads. But this is still an option, and maybe for smaller organizations, it would be a viable solution. Coming to an end, I will state a few remaining open problems we also mentioned in the paper. The first problem is that in common HPC environment, when the system is full and new user arrives, the scheduler automatically assigns user a priority. It roughly estimates when other jobs terminate and can even provide a non-destructive reservation. However, in Kubernetes, there is nothing, there are no guarantees, and the pod you just submitted can start immediately or probably an hour or never, you never know. And unless we manually adjust the priority of the new pod, unless we manually adjust the pod of the new pod to evict some running pods, we can't really do anything. There is no such thing as fair share that we know from HPC and no automation. Furthermore, there is a little problem with resource reclamation. In HPC environment, you know that the job will end sometimes and free the resources it was using. However, in Kubernetes, there is no such mechanism. Nothing really checks whether the resources were really freed. And it is a problem for some workload types, for example, deployments, which can reserve resources for unlimited time and nothing is forcing user to delete his workload. This is again a recent experience with Jupyter Hub and Jupyter Notebooks, where users didn't delete their notebooks and they were consuming not very much CPUs, but for example, a GPU, which is an expensive resource, and we really don't want that to just be allocated and not used. Second, and my last problem is the problem that causes infrastructure administrators despair. In academia, the scientific work pays itself in form of publications, acknowledgements, or similar. And therefore, it is important to correctly evaluate everyone and ask from the biggest resource users some recognition. And sadly, Kubernetes does not have any proper accounting mechanism. The accounting can be, of course, done manually, but when you have more than 200 namespaces, it is not viable, and it is not viable even before that, but it can be done. From our experience, it is not enough to warn users or show users their request to real usage ratio. It is not even enough to show them how much would their computations cost in, for example, Amazon AWS, because they know that it does not cost them anything. So it's not motivating them to do better. Therefore, we think that an overall usage policy should be defined, and some form of virtual coins or lowering or increasing priorities based on resource usage should be created. But this is more of specific to every organization, how it handles accounting. But we still think that there should be something that would motivate the users to do better. And this is the last slide. And with it, I would like to add that we will provide shortly a cleaned dataset from our Kubernetes cluster. It covers nearly 300,000 unique pods, from which nearly 2,000 are long-running, meaning they run several months. Some data inputs miss runtime period due to logging error, but it should be just a few of them. And the data includes features that are mentioned on the slide. So you can feel free to use the data set for any analysis or just to look at it and see what we are doing. And this data set will be available at the website you see, JSSP, etc., etc. And that was all. Thank you for the attention. And now I'm here with Dalibor to answer questions.
Thank you.
And I will stop sharing for a technical reason.
I do have a question if nobody else has questions yet. The Kubernetes clusters in an academic environment, I assume, is meant to support a different type of workload that what a classical HPC infrastructure is supporting, right? Could you give an example of the typical workloads that this Kubernetes cluster is supporting, like workflow managers or just academic sites? What is it exactly?
Can you please repeat the question for me?
Sure.
I lost connection.
The question is, what kind of workloads are being supported today by this Kubernetes cluster? What examples?
Yeah, I have a very up-to-date experience with Nextflow Workflow Manager. If you know that, it's a workflow manager that can run on different executors, and I've been comparing how it performs in PBS Pro, which is a great execution engine on Kubernetes and on local resources. And the preliminary results are that in Kubernetes, it's like the perfect environment for this specific pipeline we run. And if I was to characterize the pipeline, it has many components that run like for a minute and require just one CPU and a small amount of memory. And this is a nightmare for an HPC environment because the jobs are small, they have to wait in the queue. And for Kubernetes, everything is really great because they are small, so just container is deployed and done in a second. So this is one specific workload type that is actually supported in both environments, and I have been able to see that there are huge differences. And then we have been running, for example, AlphaFold, which is like a visualization tool for proteins that is now quite trendy and people like to use it. And it's interactive, so like you could do it in your batch script and sometimes visualize it, but we have it as a web application, and you just input the sequence you want to visualize, some parameters that are well known to the people who use AlphaFold, click run, and what happens at the backend is that Kubernetes type of the Kubernetes object of type job is spawned, and it's just as HPC job, but it's in Kubernetes, so it runs more quickly, and it computes this visualization, which can be CPU intensive, and then just returns it back to you. We have more like biomedical and nature-related softwares running in Kubernetes, and they all perform really nice because you create just an image with all the complexities and dependencies, and the end users are actually happy that it works, and they don't have to deal with all this infrastructure hell themselves, but they can just use it. They don't see the complexity also on the Kubernetes side, like this scheduling. This is our problem. But in the end, many workload types can be transferred to Kubernetes.
Yeah, it's interesting because what you seem to be mentioning is that most of the workloads are happier in Kubernetes, not so much because of the service-oriented nature of Kubernetes, but more because of the container, the easy way of containerizing things, which is interesting. Okay, thank you. The second question is, these workloads, I'm not sure if they are like purely service or they are like kind of intermediate between batch and service. And I think you mentioned this as an open problem. How are you managing quota? Like how is people requesting capacity? Because as you pointed out, you are allocating requested quota once is given, it's given forever, right? Unless you are doing overcommitment and then you don't guarantee placement later. How is that done?
Oh, now the new solution that we are employing to have at least some quotas is we use rancher distribution of Kubernetes, which has a nice notion of projects that is understandable to users, and you can assign a project quota. So we have decided just internally that this is the project quota, and the namespace inside the project gets the same quota. It's something that we are happy with, and we know that some people just log into the tool once, maybe see the environment and never use it, and that's still fine because their namespace quota can be used by someone else because nothing is deployed. But when the person deploys something, he can use just up to the namespace quota, which is a reasonable number for us. I don't know, let's say like 60 gigabytes of RAM, which in the huge cluster is nothing. And when a user wants to run something bigger, or he works in a team and they are doing larger work, we have set up a process that they just write to us what they need, how much they need, and we create a new project for them. And this is like a semi-manual process, but we see that it's better than giving everyone large quotas, because there is actually a very small number of people who are able to use more than what is in our default project, and people who need more actually contact us and specifically ask what they need, because they reach the limit in their default project and they instantly see that, oh, we don't, like, we need exactly 80 because 60 is too low, because we need one more pod to get there. And they tell us, please assign us a new project with 80 gigabytes of RAM. And they really use this 80 gigabytes and it's enough for them. So this is the first new solution, just internally assigning a quota.
Okay.